How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at the many electron atoms and electron configuration. So our objectives will be to apply the Pauli Exclusion Principle as well as Hunds Rule and create box diagrams to illustrate electron configurations, as well as write out quantum electron configurations as well as condensed electron configurations. So a little bit to tackle here. So introducing the fourth quantum number called spin. So the spin magnetic quantum number is denoted with a lowercase m subscript s. And turns out, where is this coming from? Well, when we were examining the bright line spectra, it was discovered that each bright line is actually two very close bright lines. So if we're taking a look at the bright line that's down over here, it's actually two separate lines that are really close together. So how is this possible? Do we have twice as many orbitals as we thought? The short answer is no. So each orbital can hold two electrons that spin in opposite directions. So what do you mean by spin? Like, you can picture an electron kind of like a top, and it could be spinning. Well, it could be spinning clockwise, much like how it is being shown in this animation where it's spinning this way, or if you were looking at it from the side, maybe it's spinning around that way. Or it could be spinning counterclockwise. Right? So if I was to look at it from the side, it would be spinning in the opposite direction. So the electrons have different spins, and that's how you get two in each orbital. They have to have different spins. So the numbers that we associate with this is either plus 1/2 for an up spin or minus 1/2 for a down spin. And that was a terrible arrow. So minus 1/2 is a down spin. So this could be, the plus 1/2 spin, and this would be the minus 1/2 spin. So the Pauli Exclusion Principle states that no two electrons in an atom can have the same set of four quantum numbers. So remember, we have the other three quantum numbers, N, L, ML, and MS. So there's no way that electrons can have the same set of four quantum numbers. So if this was my 1s sublevel, well, this plus 1/2 would be an electron with a up spin. And now if I wanted to put a second electron in there, it has to have a down spin, right? So customarily, but kind of arbitrarily, we put spin up as the first one. You might be thinking, well, why don't we put spin down? Well, we had to pick one to do, and we went with up. All right, so you start with ups, and then you do downs. So when we're taking a look at single electron orbitals and energies, like in a hydrogen atom, everything's nice and neat. All of those sublevels are degenerate. They all are at the same energies, and it's nice. But it turns out when we start introducing other electrons, things get messed up. Because electrons repel each other. They don't want to be close to each other. They both have negative charges. They want to get away from each other. So the energies associated with these sublevels start to change. So electrons, like I said, repel each other. Other orbitals are repelled and are therefore at higher energies, right? If I put an electron in that first energy shell and I wanted to put a second electron somewhere else, well, now there's this repulsion between them. So we start to get different energies at higher energies. And the different shapes affect the other orbitals differently. So the 1s is spherical. The 2s is spherical. The 2p starts to take on different shapes like a peanut, and them having different shapes affects how they repel the other orbitals as well. So things start to get pretty messy. All right, but things that are still true. One, each orbital in a subshell are said to be degenerate. And all that means is that they have the same energy. So if I take a look at the 2p sublevel, these three orbitals have the same energy as each other. So they're equivalent to each other, but they're different than the 2s over there. Because of the repulsions, we start to get some overlap between principal energy levels. So you can see 3 has been color-coded with this kind of almost pink color. So we got the 3s here, we got the 3p there, and then we have the 3d over there. But a weird thing starts to happen because of these repulsions. This 4s sublevel is at a lower energy than the 3d. So electrons are going to want to go into the 4s subshell before they actually start to fill out the third principal energy level. It gets messy, right? So first let's take a look at Hunds Rule. Hunds Rule says for degenerate orbitals, the lowest energy is attained when the number of electrons with the same spin is maximized. So we call these parallel spins. In other words, each orbital is going to get an up arrow before any arrows, any down arrows are placed, right? It's lower energy to make sure that they all have parallel spins than it is to say have them with different spins. So you're not going to see like an up, down, up. What you're going to see is they're all going to have the same spin before you start putting anything with a different spin in there. And then you also want to mind your manners. You know, I think of this like Thanksgiving. Everybody's crowded around the table and food. It's, you know, only polite to make sure that everyone gets their first serving before anybody goes back for seconds. All right. If you go back for seconds while people are still waiting to get food, you're kind of selfish. It's kind of messed up. Right. And the way to think about this is, all right, if I had to put 3 electrons in here, well, why would I put another electron in the same orbital as another electron? Electrons repel each other. This electron doesn't want to hang out. It wants its own orbital. So instead of being paired up, it's going to get its own orbital, right? So you make sure each orbital gets 1 electron before anybody gets seconds. Right, so what's that mean for the ordering? So if you wanted to, you could say like this would be the first, this would be the second electron, the third, and then the fourth, the fifth, and the 6th electron would go in there, right? So first electron, second electron, third electron, fourth, fifth, 6th electron. All right, so now which orbital do I fill, right? So you're talking about how there's overlap and it gets real messy. So what is the order that I'm going to put them in? Well, we have what we call the diagonal rule, and I kind of put a quotation around the rule because there are exceptions. But it looks like this. You write out each principal energy level and all the subshells that are in it, and then I even put like how many electrons can fit in each subshell. And now you just kind of draw diagonal lines. So first, I'm going to fill in the 1s, and then I'm going to go to the 2s, and then once I filled the 2s, then I'm going to go to 2p, and then the 3s, and so far everything kind of makes sense. But then I get to 3p, and before I fill in the 3d, I have to fill in the 4s, right? So now, after I filled in the 4s, now I can go to the 3d and the 4p, and then you didn't see it down here, but there's a 5s, and that would be what came next. So you can use this kind of trick to figure out which orbital do you got to fill in. And like I said, it's a rule, quotation marks, because there are exceptions. So let's do a little practice with orbital diagrams. So if I had lithium with 3 electrons, all right, well, I'm going to start with the 1s, which can hold 2 electrons. So I go, all right, up arrow, down arrow. I still have another electron to place. So I got to draw another orbital. I'm into the 2s now. Now I'm moving on into the 2s, and I only need 1 more electron because there's 3 total. So that's what my box diagram is going to look like, my orbital diagram. Pause it. Try them. I dare you. Don't be a chicken. All right. So now if we take a look at beryllium, we have 5 electrons to place. So the first electron, again, 1s. First electron, second electron, I filled the 1s. So I move on to the 2s, up arrow, down arrow. I've placed 4 of my electrons. So now, where's my 5th electron going to go? Well, it needs to go into the 2p. And I'm just going to put the electron there. There we go. Now, what about nitrogen with 7 electrons? Well, same deal. I start 1s, up, down. I put 2 of them. So now into the second energy level, 3rd and 4th electron. Now, all right, 2s is full. Now I got to go to the 2p. Well, I've placed 4 electrons, so now I got to place 3 more into my p sublevel. So remember Hunds Rule, up, up, up. And those are my 7 electrons. Now sodium has 11. So again, I'm going to start with the 1s. So I go up, down. I've placed 2 electrons. My 2s, up, down, 4 electrons total. Onto my p. Well, let's see. I'm at 4, 5th, 6th, 7th, 8th, 9th, 10th electron. But now I need 1 more. So now I have to go into the 3s orbital. I only have 1 more left, so I put 1 electron in that orbital. And that's how you do these orbital diagrams. Even though these boxes are unfilled, you still need to draw them out because there's 3 orbitals for the 2p sublevel. All right, so even if they end up empty, you still need to draw that. So electron configurations. going to look like this. We got 1s2, 2s2, 2p6, 3s2. What is going on there? That's how you're going to read it, right? It's 1s2, 2s2, 2p6, 3s2. So let's break it down. There's a lot of numbers and letters in here. What's going on? Well, you can see the numbers that I put in black represent the principal energy level. So that 1s2 is telling me in the first energy level. And then in the orange, that's telling you which sublevel you're talking about. So 1s, I'm talking about first principal energy level, s sublevel. And that 2, which is a superscript, it's kind of written up in the top, represents how many electrons are in that sublevel. So how many electrons are in that S? Well, there's 2, right? And you can see how many are in each of those sublevels. So the maximums, S can hold 2, P can hold 6 electrons, D sublevels can hold 10, and F can hold 14. So let's practice writing out some electron configurations. All right, I'll do the first one. So I got Li with 3 electrons. Well, I would say that's 1s has how many electrons? There's 2 there. So I'd put a 2 and then onto my 2s, and it only has 1 electron. So that would be my electron configuration for lithium. Pause it, try the other 3. I dare you. Don't be a chicken. All right, welcome back. So let's take a look at beryllium. All right, so again, I have 1s2. I've done my first orbital. Now I look at my second orbital, 2s2. I've handled my second orbital. Now I'm on to the 2p. Oh, but wait, there's only 1 electron there, so this would be 2p1. And that would be my configuration for boron. I think I might have said beryllium, but I meant boron. Nitrogen, same process. All right, start with the 1s. There's 2 electrons in there. I move on to the 2s. There's 2 electrons in that one, so I've handled that now. And now I'm on to the 2p sublevel, and there's 1, 2, 3, so 2p3. And that would be my configuration for nitrogen. Sodium, same process. I got that 1s2. I've handled that first orbital. Moving on to 2s. There's 2 of them in there, so 2s2. I'll move on to the 2p. There's 2, 4, 6 in there, so 2p6. And now I move on to the third s. I got 1. And that's how you do electron configurations. Not too bad, I hope. So condensed electron configurations, right? Some of that we might not have needed to write now. So we are most interested in the valence electrons. And the valence electrons are the outermost electrons. And they're the ones that interact with other atoms. They're on the outside, right? So they're the ones bumping into other atoms. So they're the ones reacting. They're the ones we're interested in. So the valence electrons for magnesium would be in that third principal energy level. And it's tedious and unnecessary to show the core electrons. So these ones would be the core. Anything that's not the valence electrons are the core electrons. They're not reacting. They're not the ones bumping into other atoms and making stuff happen. So we're not usually interested in them so much. And it turns out that the core electrons have the same configuration as the nearest noble gas with the lower atomic number. So for example, the previous noble gas from magnesium is neon. And neon's configuration is 1s2, 2s2, 2p6. And if we look, magnesium's core electrons are exactly that. So in order to save ourselves some time and be more efficient or lazy, whatever you want to say, I prefer efficient because it sounds better, we can do an abbreviation where we use brackets and we put the identity of the noble gas and then what comes after it. So if I'm taking a look at magnesium, I could rewrite this as saying it's bracket neon and then whatever comes after that, right? So this bracketed neon is this 1s2, 2s2, 2p6, and I didn't have to write it out. I just said bracket neon, and then what isn't neon? Well, the 3s2 makes magnesium different than neon. So, I'll walk through the first one again, and you guys see about trying it after you. So lithium, I'm looking at lithium. It's right here. The previous noble gas is helium. So I go, all right, let me put bracket helium. And then what comes after it? Well, if it's in the second period, I know I'm moving on to the second energy level, and I'm always going to start with the S sublevel, and there's 1. Right? Helium's got 2 electrons, so out of the 3 that I need to place, I just need 1 more, and that would be my condensed configuration for lithium. So try sodium and try sulfur. All right, so sodium is right here. It's got 11 electrons. The previous noble gas is neon, so I know I'm going to do bracket neon, And then again, period 3 means I'm starting with the third energy level, S sublevel. I only need to put one more electron. So boom, 3s1. Done. Sulfur, similar but different. So again, the previous noble gas for sulfur is neon. So I'm going to do boom, neon. And that represents 10 electrons. So now I have 6 more to place. So I'm starting in the third energy level. So I start 3s2. All right, that's going to get me to magnesium. And now I got to go into, well, what comes after 3s2? Let me do my diagonal rule. 3p. So I go 3p. And then how many electrons more do I need? Well, I could just count, right? There's 1, 2, 3, 4 more electrons I need to place. So it would be 3p4. And I can check. 2 plus 4 is 6, plus the 10 from neon gives me 16, and that's how many sulfur has. So I'm looking good. So summarize, can you apply the Pauli Exclusion Principle as well as the Hunds Rule to create box diagrams or orbital diagrams to illustrate electron configurations? And can you also write out quantum electron configurations as well as condensed electron configurations? I hope so. Okay, bye.